Well, good morning or good afternoon, depends on when you tune into this, I guess. Grade 11s. Listen, guys, I mean, I don't know if it's going to be a snow day. I'm recording this on Sunday night. It's snowing pretty heavy right now outside. No sign of letting up yet. It's supposed to snow till like 6 in the morning. So, anyway, there's at least a chance there'll be a snow day tomorrow. If there is a snow day tomorrow and you can still make it into school, wonderful. If everyone's there, we'll write the quiz. If you can't make it, and I don't know what the situation is with the school buses anyway. How many of you even take a school bus anymore? I'm guessing very few. Um, anyway, we'll sort of play it by ear. So if you're there, if I get like half the students there, we'll write the quiz the next time I see you. I'd rather not have like 3 different days where we write the quiz. And what we'll do is we'll just go ahead and do the next lesson. Now, if you are not there tomorrow, so for example, let's say you're in cohort B and you couldn't make it to school because of the snow day, whatever, okay, then you're going to tune into this online lesson. Okay, you're still responsible for the work that we're doing today. And isn't that great? Like during the pandemic, we have a snow day, you still have work to do. Okay, whereas under normal circumstances, we kind of miss that day. We don't have time. We can't afford to miss a bunch of days if we have snow days. So yeah, that's like missing 2 lessons. We're not going to do that. All right, so guys, yeah, I told you that we're going to move away from graphing, and I'm a man of my word. We are actually going to move away from graphing. The next thing that we do, at least it comes from the graph. So I want to explain where these equations come from, and I write some equations down for you. Yeah, and here's the deal. This is a velocity time graph. The equations I'm going to write down actually come from the graph. Okay, so I like showing you where equations come from and not just giving you equations. Now, I just want to remind you of 2 things you should know about a velocity time graph. Number 1, the slope of the line equals acceleration. Okay, so that's number 1. Now, number 2, and this got erased. The area in here equals delta D. Okay? So here the acceleration, that looks horrible. Let me fix that acceleration. Acceleration equals slope, and area underneath the line equals delta D. Good. So those are the 2 things we know about velocity time graphs, right? Now, what I've done for you is the actual line, I'll color red. This is the actual line on the velocity time graph. I'm going to label this for you. We're going to call this V1, the velocity here at the bottom of this line, and at the top, across the top over here, we're going to call that V2. So that's your initial and sort of final velocity, if you like. The time interval on the bottom, we're just going to call that T. Okay. And you can see that the slope will be A, the displacement will be delta D. And so we have, like, if you look at our list there, we actually have 5 different variables, V1, V2, T, A, and delta D. Okay, now what I'm going to do is I'm going to write down equations. And I'm going to use the properties of the graph to write down the first 2. Okay, so number 1. Number 1, we know that slope equals the acceleration, right? Well, the acceleration remember, it's the red line that I'm actually trying to color in. This red line is the velocity time graph. I only colored like the triangle and the rectangle underneath for area. We'll get to that in a moment. But slope equals acceleration. Well, the acceleration is the change in velocity divided by the time interval. Well, we're just calling the time interval t. So that is, here, let me write it. Therefore, A equals V2 minus V1 divided by time. Now, the velocities are vectors, and so is the acceleration. And I want you to notice that what is eliminated from this equation, there's one variable that's not there. Delta D is not there. See that? Like this equation here, put it in a box, that equation does not include delta D. It's just the equation for slope. and the displacement is not there. All right, so now number two. Number two, the area under the red line, which consists of this blue triangle, I'm going to call the blue rectangle at the bottom area number one. I'm going to call the purplish sort of triangle here area number two. And so the area, the total area equals the displacement, which is equal to area one plus area two. Okay, those two areas. Well, let's do area one first. The area of a box, okay, here, area one, equals length times width, right? Well, that's just equal to V1, which is the length of the box, let's say, times T, which is the width of the box. Now, area number two is half the base times the height, so it's 1/2 of the base times the height. Well, the base is just T, so it's half of T times, and the height is V2 minus V1. So this distance here is your height, and that is V2 minus V1, the amount of that height, right? So therefore, putting it all together, these two areas added up together will equal V1T, that's area number one, plus 1/2 of T times V2 minus V1. Now, long story short, there are like terms here, V1T, and if I distribute the factors, like this bracket here, the half T to both of my terms on the inside, what I'll find is I will get this guy and this guy will make like terms, okay, with my first term. So what I end up with, and I'm trying to do the math quickly, guys, you can pause this video and do it for yourself. But when I group my yellow like terms there and I distribute everything, what I end up with is half of V1T plus 1/2 of V2T. Now your book writes it like this, the common factor, the half, then they write V1 plus V2, and then they write the T like that. Okay, so I'm going to write that for you in the margin, in the box here. So I'm going to write, therefore, delta D equals 1/2 times V1 plus V2 times time. Okay, and you'll notice that what's eliminated in this case is there's no acceleration in there. Okay, so I'm going to put this one in a box. We'll call that equation number two. Okay, now, normally at this point I would show you some algebra where what I do is I play a little game where there are 5 different variables, right, in my list. Okay, if you look at my 5 variables here, let me highlight them for you. There's displacement, okay? There's V1 and V2, initial and final velocity. There's time, and there's also, of course, acceleration, which you see up here. So I've got 5 different variables in total, and I've got 2 equations. Well, these 2 equations are sufficient to answer all the questions, but I can do a little math right now that'll save me some trouble later. So what I can do is I can combine these equations to eliminate other variables. So say, for example, I wanted to eliminate the final velocity, V2. How could I do it? Well, I could combine these equations. I'll take equation number one, solve it for V2, and I will get AT. This is because I'm really good at algebra, guys. Now, if you want to go slow, figure that out for yourself. I just solved equation number one in my head for V2. I did it all in one step. And then I can substitute that into equation number two, okay? And therefore, equation number two will become 1/2 of V1 plus AT plus V1 times T. Now, these two are alike, okay? So I can combine them, that's 2V1, and then I'll get rid of the brackets. And what you'll end up with is V1T plus 1/2 AT squared, and that's equal to the displacement. Sorry, I should have written the displacement here. That's equal to delta D. That's equation number two. Or sorry, that is equation number two has become this. So now I'm going to write over here in the margin another equation, delta D equals v1t plus 1/2 at squared. I'll put it in a box, and what's eliminated this time is v2. That's been eliminated. There's no v2 in that equation. Now these are all vectors. Sometimes I forget to write the little vector hats. They're all vectors, so they include direction. All right, now, long story short, I don't want to show you all the rest of the algebra because, like, you probably don't care where the equations come from. You're just going to use them, right? So we call this equation 3 here. Well, number 4, I can eliminate v1 the same way I eliminated v2. And if I do that, I'll just put it over here in the margin. You'll get delta d, let's just skip to the end, v2t minus 1/2 at squared. And that is if I eliminate v1. So if v1 is gone, okay, from that equation. And finally, I can eliminate time. And when I eliminate time, I get a kind of an unusual equation. I get v2 squared equals v1 squared plus 2a delta d. If you don't believe me, do the algebra for yourself. But I'm right. I'm really good at this, and I know. So that, we'll call that equation 5. And here we've eliminated time from that equation. Now, some students will say, why are we eliminating these variables like this? And so now we have 5 different equations, but really there's only 2. We just did a little bit of algebra to generate the other 3, eliminating one of the variables. Okay, so now we have 5 different equations. Each equation eliminates one variable, okay, of the 5 variables. Now, why is this helpful? Well, you'll see. I've got some practice questions for you, but here, let me show you from the Running Man. Okay, remember the Running Man app? Let me show you from the Running Man an example of how we can use these equations to our benefit and advantage, okay? So let's go to the Running Man, which is should be right here. There he is. Okay, so there's the Running Man. Now let me ask you a question. I'm going to give the Running Man an initial velocity of, I don't know, 5. Let's make it 5. Okay, so I'm going to give him an initial velocity. Here's the red vector that indicates a velocity of 5 meters per second. Now, I'm going to ask you a question. He's starting out at 5 meters per second. That's v1. I'm going to now give him an acceleration, okay? And I want you to tell me the right acceleration that you would give him so that he comes to rest at his house, which is a displacement of 18 meters in the positive direction away from him, okay? So he's going to, listen to that again. We're going to set him into motion, okay? He's going to start running at 5.029 meters per second, okay, in the forward direction. We want him to run exactly 18 meters, but slow down and come to a stop when he gets to his house. And what acceleration do I plug in for A will make that happen for me, okay? So we want him to slow down, okay? So we call this a stopping problem, like he's trying to stop at his house. Okay, now let's go back to OneNote. Before we actually take guesses and we put the number in, let's go back to OneNote. And let me explain the problem again. We have our Running Man. We want him to move. Okay, we'll call this example number 1. We want him to move 18 meters forward. So we call that's a positive number. We want him to move 18 meters forward. We know our initial velocity, v1, is 5.029 meters per second forward. That was the number, right? Yes. Okay, so 5.029 meters per second forward. So that's also positive. We want him to stop, so that means V2 is 0. Okay, at his house, which is 18 meters ahead, we want him to stop. I'm asking you what acceleration would let me do that. And there's one variable I haven't mentioned, time. Well, time, we don't care what time is. I don't care how many seconds that will take. So I'm going to highlight this for you. We don't care about time. Why is that important, what we don't care about? Well, notice I've listed all 5 variables, and I've listed the one I don't care about. I don't care about time. Now, why would I write that? Well, because we don't care about time, we go to our list of equations here. One of these 5 equations doesn't have time in it. And you'll notice it's right here. This one has four of the 5 variables, but it doesn't have time. So what we do is we go ahead and we go straight to that equation. So watch. I'm going to go, okay, so therefore, v2 squared equals v1 squared plus 2a delta d. This is equation number 5. Okay, I'm going to solve it for a. Okay, a is the thing I'm looking for. I'm going to solve it for a. Now let me do some algebra for you. A will equal, I'm so good at this, v2 squared minus v1 squared divided by 2 delta d. There you go. That's what a will equal. Now, if you don't believe me, look, you're watching a video. Pause the video, do it yourself, do the algebra. You'll see I'm right. Okay, now these are vectors. Sometimes I forget the vector signs, but let's agree that they're always there, whether I remember to write them or not. Okay, now we go ahead and plug in all the numbers. So I'm going to write a is equal to 0 squared, that's just 0, minus 5.029 squared, okay, that's v1 squared, divided by 2 times 18. Okay, so now I'm going to take out my calculator and I'm going to go ahead and write 0. I don't need to square 0, but whatever, I'll just humor myself here. Divided minus 5.029. I have to do that first because in a sense, this is all in brackets on the top. I'm going to square that number. Okay, and then I'm going to divide that by 2 times 18 is 36. So I divide by 36. Let me do that again. 0.029 squared divided by 36. I get 0.703, so negative 0.703 meters per second squared. All right, so now I'm going to go back to the running man. So let's go back. Now, I don't know if I can enter a number like that. Let me see if I can. So 0.703 is negative. Oh, I'm sorry. I don't have a keyboard here, so let me try this. That's not going to work. Where's the dumb keyboard? All right, so let's try this. Negative 0.703. Let me do that. There we go. All right, so negative 0.703. Now I've entered all this information in. Let's see if he stops. Now he's not going to stay stopped in this problem. Let's see if he stops at the house. Okay, so let's press play. So here he goes. He's running forward, slowing down. Slowing down, slowing down, slowing down, slowing down, slowing down, and he stops right there. It's perfect. Okay, so he's still not quite there. Let me see if I go a little forward. Now he's actually turning around. So the deal is we wanted him to move forward but slow down so he stops at his house. And guys, we got it perfect. Okay, see, I'm not selling you stuff that doesn't work. It really works. Okay, so let's go back to this. See, that's how you do questions with the motion equations. Now let's do another one. Okay. Here, let's make it a different unknown this time. So let's go back to our running man thing. What if I made the acceleration different? Okay, so what if I tell you here for the running man, what if we turn it around? Okay, so I'm going to go back to the running man. I'm going to give him I'm going to put him right at the wall. This time I'm going to give him an initial velocity of -7. Actually, make it like, actually, why don't I type in the number and make it negative 10 meters per second. Okay, so it's negative 10. And what I'm going to do is I'm going to give him a deceleration rate of positive 3. Okay. So let me type that in. Okay, let's see if that worked. Well, that was silly. So let me do that again. Let's enter the number 3. All right, there we go. Now my question for you this time is, how far will he go? Okay, he's starting at positive 10. Okay, what will be his displacement in the negative direction? If he starts with a velocity like Usain Bolt running at 10 meters per second in the negative direction, but he has a positive acceleration. So again, he's going to slow down. How far will he go this time? So here's our setup. What's my displacement going to be? Okay, his V1 is negative 10 meters per second. His V2 equals 0, so he's still going to stop. A equals 3 meters per second squared in the positive direction. And again, time is don't care. So what we don't care about tells us what equation to use. So again, we'll use equation 5, this time solving for delta D. So delta D will equal V2 squared minus V1 squared divided by 2A. And how do I know that? I know that from taking equation 5, which I highlighted here, and isolating algebraically using my mad, great, absolutely crazy algebra skills, which you have too, of course, and just isolating the variable that I'm looking for. So I'm looking for delta D. So now I'm going to plug the numbers in. 0 squared minus. Now, my V1 is negative number, but I'll put negative 10. But when I square it, it doesn't really matter, does it? Right? And I'm going to divide that by 2 times 3. Okay. Now, I may find that he runs like right off of the picture here. Yes, I might find that actually. 100 divided by 6 is 16 meters. No, we've got room. So it's 16.7 meters. I got negative 16.7 meters. So he's going to run negative 16.7 meters. Let's see if that's true. So we go here. Now he's starting at positive 10. So he should end up at negative 6.7 before he stops. Let's see if that works, because that's 16, right? Like he's going to go 16 meters in the negative direction. So he's already facing the negative direction. Let's see what happens. So here he's running, slowing down, slowing down, slowing down, slowing down, and he stops right there. Okay. And he is like, we missed it just by a hair, but 16 point, like he's at 16.5 meters now, 0.6 meters, pretty much perfect. Okay. And of course it's perfect because, like I said, it works out perfectly. Okay, using these equations every time. Now I have a couple of other examples. This was a quiz from last year. Okay, so let's take let's do at least one more, and then I've got some practice questions for you to try. Now I'm not going to leave you hanging out to dry. Okay, it takes a little practice, but I think you're going to enjoy this. Okay, a lot more than you enjoyed the graphing. That's what I find students are like. So here we're going to read this question. Okay, so while attempting to acquire her G2, Lara is driving at 80 kilometers per hour west. Now, right away, I'm going to read that, and I'm going to write V1 equals 80 kilometers per hour west. Now, I recognize that kilometers per hour is not a standard unit. So I'm going to convert that to meters per second by dividing it by 3.6. So I'm going to go divided by 3.6. Take out my calculator. I'm going to divide 80 divided by 3.6 is 22.2. So this is 22.2, repeating, meters per second west. You must use standard units, which means meters per second. The reason why is acceleration is in meters per second squared, so it's critical. Okay. Now we keep reading. She slams on the brakes. She slams on the brakes on dry pavement and skids 45 meters. Now that is the displacement. Delta D is 45 meters. Now she's still moving forward, so that's also west. Okay. And then she comes to a complete stop. Well, if you stop, V2 is 0. Okay. Now it says, assuming uniform deceleration, which we always assume, so you don't have to worry about that. What is the acceleration of the vehicle? So they're asking us for A, and now I'm going to sound like a broken record. They're asking us for the acceleration, and again, time is don't care. So T is don't care. Now I want you to write that down every time you do one of these questions. What is the variable you don't care about? In this case, it's time. So now we're going to go ahead and use equation 5 again. And I'm sorry, it just happens to be a coincidence that we're always using equation 5. You can use one of the other equations. It just depends on what you don't care about. Okay. So now I'm going to solve it for A. So A will equal V2 squared minus V1 squared divided by 2 delta D. Okay, let's plug the numbers in. That's going to be 0 squared minus 22.2 squared divided by 2 times 45, like that. So I'm going to go ahead, square that number, divide it by 90. It's 2 times 45. I get 5.59. I'll keep 3 sig figs for those of you who care about that kind of thing. Whoops. 5.49, pardon me, meters per second squared. And the thing is, I get a negative number. So what that means is A is equal to 5.49 meters per second squared. Since it's negative, it has to be east. And that makes sense when you're hitting the brakes. You're going to accelerate in the opposite direction. All right, let's take a look at, actually, let's skip number 2 for now. I'll show you that one on another lesson. Let's do number 5. Okay. Number 5. It says here a ball is thrown up in the air. So up in the air at 10 meters per second. So I'm going to write V1 equals 10 meters per second up. Okay. From a 20-meter building. Whoops, pardon me, I meant to highlight that. From a 20-meter building top. And then it says how much time will pass before it hits the ground. All right, so let's get rid of some common misconceptions. And I need to tell you a little bit of a secret about gravity here in a second. Okay, so let me tell you about gravity right now. Whenever you throw something in the air, once it's moving through the air, the acceleration is gravity's acceleration, and gravity has an acceleration of 9.8 meters per second squared down. Gravity's always down, and it's always on Earth, 9.8. Okay? The question doesn't tell you this, but it's a known number. Okay? So every time something's in free fall, you may use that number. The question won't tell you. We know it. It's Earth. That's what it is on Earth. Okay? All right. Now, what's V2? Well, it hits the ground. Please don't write V2 is 0. V2 is not 0. It's the impact velocity. So in other words, it's the velocity just when it hits the ground. And that's not going to be 0. Like if, let's pretend, okay, let's say, for example, Luna was standing outside St. Matt's, and I'm standing on top of the building and I drop a water balloon on her. Maybe we can try this experiment, okay? So I drop a water balloon on her from the roof of St. Matt's. When it hits her in the head, it will not hit her at a speed of 0, okay? It'll hit her with a certain amount of impact, and that will not be 0. But here's the thing, we don't care what that impact, as long as it hits her, right? Because, you know, that'd be some certain amount of fun. Maybe we could all try it, okay? We'll all take a water balloon up there and we'll do several experiments. Okay, so look, the point is we don't care what it is. Okay, so in fact, that's going to come in handy later. So the impact velocity is not zero. Please, when it hits the ground, do not assume it's zero. It's not zero. Okay. All right. What about the 20 meters? Well, that's the displacement. It's 20 meters, but it's down. Now, how do I know it's down? Well, we'll get to that in a second. It's asking us for time. So it's asking us for time. And we'll get to why it's 20 meters. Let's say you're standing on top of a building, okay? And a ball is thrown upwards. So what's happening here is there is someone standing on the building. Let's say it's Hader. Okay, so here's his little hair. There's Hader. Okay, and what he's doing is he threw this up in the air, but it's going to go up and then it's going to come back down. Okay, now here's the thing. The equation describes the whole thing. We know the displacement is 20 meters down, so that's delta D. Now remember, yes, it goes up first, but we don't care what the distance is. It started there, it landed here. All we care about is the difference between where it starts and where it ends for displacement, and it's 20 meters down. So please don't break it into two parts, the upward part and the downward part. Please don't do that. Okay? Anyway, it's 20 meters down. And here is where it has a V2 that we don't care about. We could find it though, the impact velocity, if we wanted to. We could use a motion equation. We could care about it and find it, but we don't care. What they're asking is for how much time this takes. So you understand what we're doing. All right. So now we have a decision to make. I'm going to make down positive. Why? I'm going to circle this with a rainbow. Down is positive, which means this upward guy is a negative number. But my other vectors like gravity and the displacement, they're both down, they're positive then. Okay, so since down is positive, therefore V1 equals negative 10 meters per second. See, one is up and the other ones are down. We have to care about the direction in these equations. They are vector equations. Now, in which equation do we not care about V2? Well, actually, we go up to our list of equations, way up here. The one that doesn't have V2 in it, I'll continue with my rainbow, is equation 3. Okay, so you go back down to our sample problem. I'll write equation 3, delta D equals V1T plus 1/2 AT squared. Now I'll fill in the numbers. Positive 20 for the displacement. Gosh, pardon me. Positive 20 equals negative 10t, and then it's going to be plus 1/2 times 9.8 times t squared. Okay, so let me simplify that a little. 20 equals negative 10t plus 4.9 t squared. How do I solve that for time? Well, you're not going to like this answer very much, but it is something you learned in grade 10. This is a quadratic, okay? I'm going to put it in standard form for you. Normally you use x for a quadratic. Let me put it in standard form. It's going to be 4.9 t squared minus 10t minus 20 equals 0. So if you want to think of it as a quadratic, 4.9x squared instead of t minus 10x minus 20 equals 0. Now do you get it that it's quadratic? So it doesn't get any better, guys. I can just picture your faces. Use the quadratic formula. Oh, I love teaching physics. I love teaching all of you also, okay? It's going to be negative b plus or minus b squared minus 4ac, this is what the time will equal, divided by 2a. Now, what are a, b, and c? Well, let's come back to this. 4.9 is a, negative 10 is b, and negative 20 is c. So come back to our equation. I'm going to get negative b, which is 10. Is it 10? Yes, it's 10, right? He throws it up at 10 meters per second, am I right? Yeah, he throws it up at 10 meters per second. Okay, so it's 10. The negatives cancel out, plus or minus. This is going to be 10 squared minus 4 times 4.9 times c, which is negative 20. And that whole thing is divided by 2 times 4.9. All right. Oh, I love the quadratic formula. Don't you? Okay. I always do the discriminant first. And if you're wondering what the discriminant is whatever's under the square root sign. So I take out my calculator, I go 10 squared. It's going to end up being plus because there's a negative and a negative. So it's plus 4 times 4.9 times 20. And I get 492. I take the square root and I get 22.18. So this, whoops, that works out to 22.18. So now I'm going to go, that's after I take the square root. So now if I go 10 minus that, I'll get a negative number. So I don't want to do that. I can't have a negative time. So the answer can only be positive. So it must be positive because negative time makes no sense. Okay, so therefore the time will equal 10 plus 22.18 divided by 2 times 4.9 is 9.8. Okay, so plus 10 divided by 9.8. I get 3.28 seconds. Isn't that beautiful? Guys, I feel like your enthusiasm and excitement for this process, I feel it. Even though it's online video, I know like you're going to be excited when you watch this. Okay, so now I've given you a few problems. On purpose, I'm going to skip 2 of the problems on this little practice quiz. They're the 2-step problems. We're going to come back to those. So as long as you know the process for solving an equation, you have to write down the variables. The one you don't care about tells you which equation to use of our 5 equations. I will always give you the 5 equations like I gave you here. Okay. And then you just have to write down the given information and then pick the right equation and solve for the unknown that you're looking for. Now, after I've said all that, I have a little assignment for you. I don't want you to do the other 2 questions on this quiz, so leave that, okay? But I do have a worksheet for you. I've posted the worksheet on OneNote. There are a total of 7 questions. Actually, no, there are more than that. There's like 7 plus there are like 5 more at the top. So there's like 12 questions there, 13 questions. So can you go ahead and try these? Some of them are super easy. And there's a couple of them at the end that require more than 1 step. Okay. So some of them, like number 1, will just take a moment to do it. But like I said, write down the information. Don't forget to convert those. You have to divide by 3.6 to convert kilometers per hour to meters per second. Please don't forget to do that wherever you see kilometers per hour. Okay, super important. And that's it, guys. So listen, if it's a snow day, enjoy your time. You've got a little bit of a break, I guess, if you're in cohort B. If you show up for class, I will teach you these things live. If you are, and maybe we'll do a little more. If you're looking at this at home, okay, that's what you've got. So I want you to try as best as you can to answer these questions, at least the level 1 questions. The level 2 questions are a bit more tricky, but give them a shot at least. Don't kill yourself. Like, okay, if you spend 15 minutes at least, okay, trying a problem, and then you're stuck, at least you try, okay? If you spent 3 seconds looking at it, you didn't really try. Okay, so don't give up on the 2-step problems. Give it a shot, okay? And then I will help you do the 2-step problems in the next lesson. but not for today. I think we've done enough for today. So for homework, get these first 6 questions here. I know they're not they're numbered, not in a way that doesn't make a lot of sense, but then there's 2 number 2s. Doesn't matter. Okay, I kind of like doing that. It's kind of irritates like the certain type of personality sometimes. But anyway, yeah, don't worry about it. I just cut and paste these from different things. That's why it's like that. All right, so having said all that, please do these questions, and let me show you where we are in the outline. We've just done the motion equations, and so I would like you to do for homework, I would like you to do the worksheet I gave you, okay? So there is a worksheet that's called a handout here in this picture, but I'd also like you to do those questions there, okay? So that gives you like a certain amount of practice. The next quiz that we'll do this week will be just on this and nothing else. So guys, enjoy the snow, and I will talk to you very soon, okay? Have a good day. We'll talk to you, or have a good night, or whenever you're watching this, and we'll talk to you soon.